Hello and welcome to today's class. For today's class, we'll be looking at complex number, and specifically, we're talking about the polar form of complex numbers. Now, recall that in our previous class, we talked about complex numbers being represented in different forms, in rectangular form, in polar form, in Euler's form or exponential form, etc. For today's class, we'll be focusing on the polar form of complex numbers, and we'll be doing some solvings from the polar form of complex numbers. If you missed our previous class on complex numbers, simply check the description of this video and I'll provide a link to our previous class on complex numbers. But let's dive right into this. So please, if you missed our previous class on complex number, do well to watch that class first before watching this one here so that it will aid your understanding. All right. Having said so, let's look at complex numbers in polar forms. Specifically, we'll be looking at how to multiply and divide complex numbers in their polar form. The idea of this is that it will help us to understand some certain concepts in Argand diagram, which will be treated much more later. So for this first, let's recall what we said. We said in polar form that a complex number z is equal to r into cos theta plus I sine theta. When we said r is called the modulus or the magnitude, and we said r is called the modulus of the complex number. We said modulus or the magnitude of the complex number, and we said theta is called the amplitude. Now, another name for amplitude is also called the argument. Another name for amplitude is argument. So theta is also called the amplitude or the argument, which is simply the angle there. All right. In the last class, I didn't mention that theta is called argument, so you can just note it for this class that theta is also called argument. All right. Let's look at something. Let's look at how to multiply and divide complex numbers. So let's look at something. Let's say you're given a complex number. Let's say we're given two complex number. The first one is z1 being equal to r1 cos theta 1 plus I sine theta 2. So here's my first complex number, and the second complex number z2 being equal to r2 into cos theta 2 plus I sine theta 2. So I have these two complex numbers. If I were to find their products, z1 times z2, so I'll have that z1 multiplying z2, or simply z1 z2 will be equal to this multiplying this. That will be r1 into cos theta 1 plus I sine theta 1 multiplying r2 into cos theta 2 plus I sine theta 2. So I have this. So if I multiply this, what do I get? This is equal to, first things first, I'll be having r1 times r2. That becomes r1 r2. So r1 r2. So I'm done multiplying these ones here. That's the modulus. Next, I'll multiply the terms in brackets. So my first term in the first bracket, that's cos. That becomes, this is into, the first term in the first bracket is cos theta 1 multiplying everything in second bracket. That'll give you cos theta 2 plus I sine theta 2. Right, so first thing here, multiply everything in second bracket. Next up, plus second term in first bracket, I sine theta 1, multiply everything in the second bracket. That's cos theta 2 plus I sine theta 2. We have this case. All right, so simply multiply the modulus r1 r2, use the first term here cos theta 1, multiply everything here. Next up, use the second term here, multiply everything here. All right, work this out. This is equal to so that's equal to this one here, r1 r2 all into cos theta 1 times cos theta 2 gives you cos theta 1 cos theta 2 plus cos theta 1 multiplying I sine theta 2 gives you just an I here. So I into this cos theta 1 sine theta 2. Okay. Use this to expand this. So plus I sine theta 1 cos theta 2. So my I first. So I want to take cos before sine. It's the same thing whichever way. So you can choose to take sine before cos. The same thing. So cos theta 2 sine theta 1 plus. So plus I now have I times I. That gives you I squared. So plus I squared into sine theta 1 multiplying sine theta 2 gives you sine theta 1 times sine theta 2. So I have this one here. All right, so this is my case on expansion. Next up, we'll try to simplify this. So if I try to simplify this, I have R1, so that's equal to, that means Z1, Z2. So Z1, Z2 is equal to, what do I get? R1, R2. So I have R1, R2 into, for the case of time, I'll simplify everything here. Now what I mean is this. From here, if I multiply I squared, I know that I squared will give me minus 1 because we said so in a previous class. We said I is equal to square root of minus 1. So if I square I, it becomes all of this squared such that the square and the square will cancel square root. I have minus 1. Hence, this one here will give me a value of minus 1. So I have minus 1 here, multiplying all of this such that if they multiply, I'll be having cos theta 1, cos theta 2. So into cos theta 1, cos theta 2 into plus times minus 1 is minus 1 times this is itself. So that becomes minus sine theta 1 sine theta 2. All right, so I have this. All right, so minus 1 times this gives you minus theta 1 or minus sine theta 1 minus sine theta 2. Now take the imaginary part, that's the i's. So I have this one here. So plus I into the first one here is cos theta 1 sine theta 2. That's cos theta 1 sine theta 2. And then a final I, so plus I. So plus I into cos theta 2 sine theta 1. So we have this one here. All right, so if you have this case here, we can choose to factorize the i's. Okay, let's factorize the i's. We'll have that z1, z2 is equal to r1, r2 into, I'm having this one here as cos theta 1 cos theta 2 minus sine theta 1 sine theta 2 plus I into, factorize the i's. I'm having this as cos theta 1 sine theta 2. I'm going to write this properly. And then this one here plus cos theta 2 sine theta 1. So I have this when I simplify. So I have this one here. All right, so we are now at this point after expanding this one here. That's multiplying two complex numbers in surd form or in polar form, please. Two complex numbers in polar form. My next start would be, from this, I can see a trigonometric identity. Remember that from trig functions, we said cos, that's how we cos. We said cos A plus B. This is a trigonometric identity, is equal to cos A cos B minus sine A sine B. This is a trigonometric identity. We also have that sine A plus B is equal to sine A cos B plus cos A sine B. All right. So with these two ideas now, we can write this multiplication or this product in this form, such that I'll have that Z1 Z2 is equal to R1 R2, that's R1 R2 into I have cos. Now observe that if this was A and B, if theta 1 was A, I'd have had cos A, theta 2 is B, I'd have had cos B minus, we said theta 1 should be A, so sine A, and then this would be sine B. So observe that these two things are the same thing, all right? Cos A, theta 1, cos B, theta 2, minus sine A, theta 1, sine B, theta 2. That means I can write this as being cos into, in this case it was A and B, but in this case I use theta 1 and theta 2, so it becomes cos theta 1 plus theta 2, the same concept. All right, so that's just this. That's just writing this one here in this form, but in this case I'm using theta 1 and theta 2 and not just A and B. So plus, my next tag says I, so I have I. Similarly for this one here, if you observe this, I have that sine A plus B is equal to sine A cos B plus cos A sine B. That's the same thing as this one here. As you can see this, let's call A to be equal to theta 1 and B to be equal to theta 2. So that would be sine theta 1, which is this, cos theta 2, which is this, plus cos theta 1, which is this, sine theta 2, which is this. All right, so these two are the same thing. Although they're not arranged in the same form, but it's the same thing, because this is called the commutative law of mathematics. So although they're not arranged perfectly as this, but they mean the same thing since they're multiplying. So hence, this one here, this whole thing here, can be rewritten as sine. Now we said theta 1 is A, so it becomes sine theta 1 plus B is theta 2, so theta 2, I have this. All right, so this becomes the answer. So that means if I'm multiplying any two complex numbers in polar form, the idea is simple. Multiply their modulus, open bracket, cos, add their argument or their amplitude, plus I sine, add the second value of the amplitude, and etc. So this is simply how we multiply two complex numbers. We'll take a quick example and we'll do this. So with this now, example, let me say I had Z1 as being equal to 3 into cos 45, or let's say 42, plus I sine 42, and I had Z2 as equal to 3 into cos 5 plus I sine 5. And I'm asked to find, of course, this is in degrees. So in degrees, and also in degrees. So I have this. So I'm asked to find the value of Z1 and Z2. So Z1, Z2 will simply be equal to R1, R2. R1 here is 3. R2 here is 3. Okay? That becomes 3 times 3, which is what there? 9 into, I will now have cos of, in this case, theta 1 is 42, theta 2 is 5. So it becomes 42 plus 5, 42 plus 5 plus I into sine. Of course, theta 1 here is still 42. So 42 plus theta 2 here is still 5. So I have 5, all in degrees. And my final answer will be equal to 3 times 3. 3 times 3 here, which is 9, into, I have cos 42 plus 5, 47 degrees, plus I sine 42 plus 5, 47 degrees. So this would be my final answer after multiplying these two complex numbers in polar form. So this is how we multiply complex numbers in polar form. All right. All right, so this is how we multiply complex numbers in polar form. So let's look at the multiplication of complex numbers in polar form. But this one here was in degrees. So let's what if it is in radians? Look at how to also multiply complex numbers when they are in radians in our next example. All right, let's take a second example. So let's say we are given z1 as being equal to 9 cos theta over 3 plus I sine. So let's say we are given z1 as being equal to 9 into cos pi over 3 plus I sine pi over 3, and z2 as 11 cos pi over 2 plus I sine pi over 2, and we asked to find the value of z1 multiplying z2. So how do we solve this? Remember that we said, let's recall something. Recall that we said z1, z2, we said z1, z2 is equal to r1, r2 into cos of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. We had this one here. So the idea was simple, that z1, z2 is equal to multiply the two modulus, so 9 times 11 into cos of theta 1 plus theta 2. That becomes the angles. So the angle now is in terms of radian, no longer degrees, but I'm still adding them anyways. So this all over 2. So add this plus I sine, having this one here, theta over 3 or pi over 3 plus pi over 2. So it's quite simple. Just add these and let's see what we get. So if we work on this now, this is equal to 9 times 11 is 99. 99 into, I'm having cos, take the LCM here. My LCM here, 3 and 2 is 6. So 6 over 3 is 2 times pi is 2 pi plus 6 over 2 is 3 times pi is 3 pi. So I have this plus I sine, take the LCM of 3 and 2, and that again is 6. 6 divided by 3 is 2 times pi is 2 pi plus 6 divided by 2 is 3 times pi is 3 pi. So we have this. Alright, so it means that z1, z2 is simply equal to 99 into cos into cos 2 pi plus 3 pi gives you 5 pi all over 6. So I have this plus I sine, I have 2 pi plus 3 pi, that's about 5 pi all over 6. So I have this. So this becomes the answer in radians. So this is the value of z1, z2 in radians. If you're asked to provide this value in terms of degrees, all right, they say leave your answer in terms of degrees. What do? Very simple. We said 1 pi is equal to 180 degrees. So simply replace pi as 180 degrees there. We'll have that z1, z2 is equal to 99 into cos 5 times 180, that's pi 180 all over 6 plus I sine 5 times pi 5 times 180 over 6. So we have this value. Now let me clarify something before we proceed, please. The value of pi in angular measurement is 180 degrees. But in other branches of mathematics, like when we talk about mensuration, pi is equal to 22 over 7. That's like 3.14 whatever there. All right, but that's not in this case. In terms of angular measurements, degrees and radians, pi is equal to 180 degrees. We talked about this in our previous class. All right, let's simplify this. So it means that my final answer, z1, z2, will be equal to 99 into, I'm having this as cos 6 here 1, 6 here 30. 5 times 30 is 150. So 150 degrees. This plus I sine 6 here 1, 6 here 30. 5 times 30 is 150 degrees. All right. So this becomes the value of z1, z2 in terms of degrees. All right. So this is how we solve the multiplication of complex numbers in polar form. Next up, let's look at the division of complex numbers in polar form. All right. So let's now look at how to divide complex numbers in polar form. So let's check out the division of complex numbers in polar form. Let's say we're given our first complex number in polar form as z1 equal to r1 cos theta 1 plus I sine theta 1, and z2 being equal to r2 cos theta 2 plus I sine theta 2. We asked to evaluate the quotient z1 over z2. So for this one here, I won't really go into the derivation of the formula as I did for multiplication. So I'll just give you the final answer of how it works, and we can take some few examples and proceed. Z1 over z2 in polar form is equal to r1 over r2 into, that becomes cos of theta 1 minus theta 2 plus I sine theta 1 minus theta 2. So we have this case here. We'll have this case. All right. So this is how, or this is the formula that helps us to do the division of complex numbers. All right. It's kind of similar to multiplication, just that for multiplication, these two, I'm actually multiplying them, but for division, I'm dividing them. These two, for multiplication, I am adding the angles or the amplitude or the arguments. For multiplication, I'm subtracting the angles and not adding them. All right, so that's how this works. Let's get an example. Let's say example. Let's say example one. Z1 is equal to 5, or let me use something like 15. 15 into cos 9 degrees plus I sine 9 degrees, and then I have z2 as being into 3, as being equal to 3 of cos 5 degrees plus I sine 5 degrees. So I have this. I'm asked to find z1 over z2. Obviously, z1 over z2 will be equal to, we said, divide the modulus. That becomes 15 over 3 into cos, subtract the angles, 9 minus 5. So I have 9 minus 5, all in degrees, plus I sine 9 minus 5. So I have 9 minus 5, all in degrees. If I work on this, 15 divided by 3 gives you 5. So I have 5 into this one here. That becomes cos 9 minus 5 is 4 degrees plus I sine 9 minus 5, still another 4 degrees. All right, so this is how we divide complex numbers in polar form. We'll look at, now this was working with degrees. Let's work with radians, and then we'll be done with this. So example 2. So example 2, let's say z1 is equal to 11 into cos pi all over 2 plus I sine pi over 2. So we have this as Z1. And let's say we have Z2. So we have Z2 as being equal to 88 into cos pi all over 5 plus I sine pi over 5. Let's say we had this one here. We have to find the value of Z1 over Z2. So from here, Z1 over Z2 will be equal to, we said divide this, so it becomes 11 all over 88. So Z1 over Z2, that's R1 over R2 into cos theta 1 pi over 2 minus theta 2 pi over 5 plus I sine theta 1 pi over 2 minus theta 2 pi over 5. So I have this expression. So I'd have to work on this. This will be equal to, this is equal to, that's equal to lowest term, 11 here is 1, 11 here is 8. That gives you 1 over 8 into, I have this as take my LCM here. The LCM of 2 and 5 is 10. My LCM is 10. My LCM here is 10. So 10 divided by 2 is 5 times pi is 5 pi minus 10 divided by 5 is 2 times pi is 2 pi. We have this one here plus I sine, we have this one here. LCM of 2 and 5 is 10. So 10 divided by 2 is 5 times pi is 5 pi minus 10 divided by 5 is 2 times pi is 2 pi. So we have this one here. All right. So that means that Z1 over Z2 on final simplification, this gives you 1 over 8 into, I'm having this as cos, so cos, work on this, 5 pi minus 2 pi gives you 3 pi all over 10, so I have this, plus I sine 5 pi minus 2 pi is 3 pi all over 10. So I have this answer. All right. So this is how you divide two complex numbers in polar form. All right. If you want to, now of course this one here is done in radians. That's why we use pi. If you want to convert this answer to degrees, simply substitute pi as 180 and do your solving. All right. And then you have your answer. All right. So this is how we do this work. Before we go, one final thing I'll show you is how to convert a complex number from polar form to rectangular form, right? We've seen how to convert from rectangular form to polar form. Now let's look at how to convert complex numbers from polar form back to rectangular form, and then we'll call it a class. Okay, so finally, let's look at how to convert complex numbers from polar form to rectangular form. So in our previous class, we looked at how to convert complex numbers from rectangular form, or you can say the Cartesian form, to the circular or polar form. But for this video, we're looking at how to convert it from polar form back to the rectangular or Cartesian form. But before we do that, let's take a very simple example, a brief one. We said if z in rectangular form, if a complex number z is equal to 1 plus I, for instance, that to convert this one here to a polar form, we need to find two things. The first one we said is the magnitude or the modulus of this complex number. The second one we said is the amplitude or the argument of this complex number. So first things first, let's find the modulus or the magnitude of this complex number. So we said the modulus of the magnitude r is simply equal to the square root of what I have here, 1 squared plus the imaginary part, coefficient here is 1 squared. So we did this in our previous class, and we said r is equal to the square root of 1 squared is 1 plus 1 squared is 1. That's equal to the square root of 2. So I have root 2 as my modulus or my amplitude. Next up, we said theta as my modulus or my magnitude. So we said theta, which is the argument or amplitude, is equal to tan inverse of b, that's coefficient here, which is 1 all over the number I have here, which is 1. So we discussed this in our previous class, and that will be equal to 1 over 1 gives me 1, tan inverse of 1, let me punch that, tan inverse of 1, the answer is 45. So I have 45 degrees as the argument or the amplitude. So therefore, in polar form, z will be equal to r into cos theta plus I sine theta. So z then is equal to r here is root 2, so it becomes root 2 into cos theta. That becomes into cos. We got theta here as 45 degrees, so 45 degrees plus I sine theta, which we said is 45 degrees. So this becomes the polar form representation of this complex number. So what if I was given the complex number z being equal to root 2 into cos 45 degrees plus I sine 45 degrees. This is in polar form, and I was asked to convert it back to the rectangular form. What do I do? Now, the idea is simple. The concept would be express these ones first in either decimals or surd or whatever. Just find the value of this and this. Then use the magnitude or the modulus to multiply through. So it means that z will be equal to square root of 2 into cos 45. If I punch cos 45, my answer is 1 all over root 2 plus I sine 45. Sine 45, the value is 1 over root 2 also. So 1 all over root 2. So put this in round bracket, change this to square bracket, and then this. All right. So cos 45 gives me 1 over root 2. Sine 45 gives me 1 over root 2. So if I multiply this, it means that z will be equal to, use this to multiply this, it becomes root 2 multiplying this one here, 1 all over root 2 times, use this to multiply this, but first of all have your I, so it becomes I, use this one here to multiply this, it becomes root 2, so dot root 2 times 1 all over root 2. So I have this answer. So hence z will be equal to, of course, this becomes root 2. Root 2 times 1 is root 2 over root 2 plus I into root 2 times 1 is root 2 all over root 2. From here, it means that z is equal to root 2 divided by root 2 gives you 1 plus I into root 2 divided by root 2 gives you 1. So into 1, multiply this. It means that z is equal to, I have 1, so it becomes 1 plus I times 1 is I. So I have I. So z is equal to 1 plus I. That's the exact thing we had from here. That z being equal to 1 plus I. Alright, so this is how you convert from rectangular form to polar form, and from polar form back to rectangular form. Alright, so this is how you do this. We'll take one more example on this, and we're done with today's class. Alright, so let's look at the final example on how to convert complex numbers from polar form to rectangular form. In this case, we'll be considering the polar form in radians mode or in radians form. So we have convert z being equal to 15 cos pi over 5 plus I sine pi over 5 to rectangular form. That's missing here. So to rectangular form, leaving your answer in the nearest hundredths, right? All right, so let's get this done. How do you convert this one here to rectangular form, leaving your answer in the nearest hundredths? That would be easy. So your first task would be, if you know how to work with your calculator, the task would be you can directly punch cos pi over 5 in with your calculator, you have your answer directly. That's if you can convert the calculator from degrees to radian. So you should know how to do that. I will show you how to do the conversion from degrees to radians in our calculator hack class. All right, so just simply check the description of this video and you'll see how to punch your calculator from or to convert your calculator from degrees to radians so you can punch this directly. But then let's go back to this. So let's say we cannot do that. All right, so what do we do? So let's first of all convert to what the degree form before we solve this. So first of all, convert this to degrees. We know that pi is equal to 180 degrees. So my task would be this. It means that z would be equal to 15 into cos. So cos pi is 180. So 180 all over 5 plus I sine 180 over 5. So I have 180 all over 5. So I have this one here. All right. So from this, it means that z is equal to 15 into cos 180 over 5. That's 36 degrees. 36 degrees plus I sine 180 over 5 gives you 36 degrees. So we have this one here. So from this, it means that z will be equal to 15. I'll simply punch cos 36. So cos 36, cos 36. That's about, they said your final should be in the nearest hundred. By hundred, we mean 2 decimal places, because in decimal places, let's say we have a, b dot, c, d, e. This is your nearest tenth, nearest hundredth. So when we say nearest hundredth, it's simply 2 decimal places. For this one, I would advise that you punch this one first in 4 decimal places. So cos 36 in 4 decimal places becomes 0.8090 in 4 decimal places plus I into sine 36. Sine 36 is about 0.5878 in 4 decimal places. So perhaps change this to square bracket. So I have this. So that's equal to my final answer. I can now multiply this by 15. So 0.8090 times 15. That's about 12. So it becomes 15 times this. That's 12.14 to the nearest hundredth or to the nearest 2 decimal places plus I into 15 times this number. That's 15 times 0.5878. That's about 8 points. That's about 8.82 to 2 decimal places. So therefore, in rectangular form, z is equal to 12.14 plus 8.82i. So I have successfully converted this from polar form to rectangular form. All right. So this is as much as we can take in this class. In the next class, we look at the concept of Argand's diagram and see how Argand's diagram help us to do a lot of stuffs in complex numbers. All right then. So see you in our next class.